Thanks everyone for being here. My name is Anne, a PhD candidate at the University of Washington. I'm super excited to present our paper, EquiTensors, Learning Fair Integrations of Heterogeneous Urban Data. I will start with introduction, then I'll introduce EquiTensors, an algorithm that transforms a wide range of urban datasets into one single data representation, and at the same time remove the effect of sensitive information such as race. Downstream urban prediction models can use such data representations to improve accuracy while limiting exposure to biased signals. At the end, I'll present the summary and discuss limitations and future work. Predicting dynamic urban activities such as energy consumption, air pollution, travel time, and traffic flows has become critical for improving our life. Machine learning algorithms have been employed in various urban applications to predict demand and guide resource allocation and service provision. For example, Uber forecasts demand to direct drivers to high demand areas. They use spatial temporal prediction to increase trip count and earnings. Another example involves online shopping. Amazon uses AI to help to put products as close as possible to the people who will buy them. In public safety domain, law enforcement agencies use historical data and machine learning to predict crime instances. Although these systems have already been adopted in police forces around the world, this practice is extremely controversial. We mention this case because it is technically interesting, not ethically. The aforementioned examples are typical machine learning-driven applications for cities. There are many more examples like this, such as predicting bike-share demand and traffic flow. They have a few things in common. First, they are mostly city-scale applications. Second, urban activities usually exhibit complex spatial and temporal patterns. For example, taxi demand is associated with rush hours, and the neighboring regions may have similar taxi demand patterns. Third, urban events often have complex interactions with many other factors, including temporal factors such as temperature and rainfall, spatial factors such as road network and house prices, and spatial temporal factors such as traffic collisions. Prediction models often use these external signals to boost performance. However, it is not trivial to decide which factors affect which applications because the city is a very complex system. Everything sort of depends on everything. What is more, many of the urban applications have fairness concerns. We observe that urban applications are potentially influenced by a common set of factors, including traffic conditions and the weather and house prices. These factors are more or less correlated with each other, and it is hard to know which factors are more or less important for different applications. Especially, we now have a lot of non-experts who don't have domain knowledge trying to do the predictions. Traditionally, each application will go out and collect every dataset for its own use. The process is repetitive and costly. We propose an algorithm to integrate these urban datasets into a single data representation so that the representation can be reused across many applications. The idea is similar to pre-training word embeddings for various downstream tasks. Although word embeddings are very powerful, one caveat is that it may contain human-like bias. This is problematic because machine learning algorithms can reproduce the biased signals embedded in the data. In fact, evidence has shown that algorithms used in urban applications may discriminate certain groups of people. We mentioned the Uber case a moment ago. For example, neighborhoods with more white people experienced higher levels of service quality, such as shorter waiting time. In online shopping, Amazon's same-day delivery services were found to exclude predominantly Black neighborhoods in several large cities. In public safety, a predictive policing tool called Campus was found to have notably higher false positive rates for Black defendants than for white defendants. And there are heated debates on the discriminatory effects of predictive policing tools and whether the use of such tools is appropriate at all. Therefore, on top of our integrated representation, we propose an additional module to remove any association with a sensitive attribute from the learned representation in the hope of avoiding polluting the downstream tasks with biases. Formally, this paper proposes to learn fair and integrated representations for cities. To achieve our goal, we have three contributions targeting at reusability, accuracy, and fairness. First, we want a data representation that is reusable across many downstream applications. To do that, we develop an unsupervised core integrated model based on a convolutional denoising autoencoder to incorporate as many as possible commonly used urban datasets into a single representation. The second challenge lies in how to balance the learning of multiple datasets into one model and improve the overall fidelity of the learned representation. We adopt an adaptive weighting strategy, which is inspired by existing work in multitask learning. Lastly, we use a fairness component on top of the core integrated model to remove bias from datasets. Looking ahead, EquiTensors is a novel way to allow downstream applications, a means to improve accuracy, avoiding data discovery and preprocessing, and limiting their exposure to new sources of discriminatory bias. Now, let's look at the high-level overview of EquiTensor. EquiTensors are learned representations from multiple urban datasets, such as temperature, streets, and 911 calls. They can be incorporated into downstream prediction models, say backshare prediction, directly as features, replacing traditional features such as weather and point of interest. We can regard it as a feature that represents the status of a city in a given time period. The goal of EquiTensor is to boost the accuracy of downstream predictions without introducing much extra bias. Our paper is related to three areas. Representation learning has been effective for specific urban applications such as traffic prediction and driving behavior analysis, but our focus is on application agnostic representations, and we want to maximize the reusability of the learned representations. Our paper is related to multitask learning because we want to encode and decode multiple urban datasets in one model. Some multitask learning models use task relationships to optimize feature sharing, but model complexity usually grows with the number of tasks. Another approach is to balance the loss terms across tasks to improve performance for all tasks. Our adaptive weighting is inspired by this live approach. But the difference is that multitask learning is supervised and tasks usually share one input. However, our representation learning is unsupervised and we have multiple inputs. Unsupervised learning and adversarial learning have been used to learn fair representations, but most of them focus on classification settings and only deal with categorical sensitive attributes such as gender. We adapt methods in adversarial learning for fairness to predict continuous and spatially distributed sensitive attributes. For example, a map of income distribution over a city, as opposed to only a categorical value. Overall, no existing methods attempt to integrate many heterogeneous datasets for broad reuse in many downstream urban applications or learn fair representations for spatial temporal settings. For this project, we used Seattle as a case study. We collected dozens of open datasets from a variety of portals. We used them to generate the Seattle EquiTensor. To process spatial temporal datasets such as backshare demand, we partition a city into square regions so that the spatial temporal data will be formatted as videos. Each square region has some timestamp. It's like a pixel in a video frame. For all the datasets, we project them onto a common spatial temporal grid so that they align with each other. I test the usefulness of EquiTensor in several downstream tasks. They are predicting backshare demand, reported crime instance, fire 911 calls, and the bike count over Fremont Bridge. Fremont Bridge is a bridge in Seattle. Backshare and crime prediction are used as cases in learning fair representations as well. For spatial temporal tasks, we use a model architecture based on 3D convolutional neural network. For the temporal prediction task, we use a sig-to-sig model. Now let's dive into the model architecture. The first part of the EquiTensor is a core integrated model. It is based on a denoising convolutional autoencoder, which is a popular method in representation learning. As the figure shows, the model consists of two parts, an encoder and a decoder. The encoder encodes a lot of urban datasets of different shapes into a latent representation Z. Z is the version of EquiTensor without fairness. The decoder part of the model tries to reconstruct every dataset from Z. The objective of this model is to minimize the total reconstruction error. The core integrated model assigns equal weights to all datasets during training, but the learning process can be dominated by easy datasets with strong signals. To solve this problem, we use an adaptive weighting scheme that adjusts the weight of loss of each individual dataset dynamically during training according to its learning progress. We assign larger weights to datasets that still have a long way to go before they converge. We determine learning progress based on the ratio of current loss to an optimal loss for that dataset. The optimal loss is approximated by the reconstruction error of an autoencoder trained separately for that specific dataset alone. When the loss for the current step is high relative to the optimal loss, then the dataset receives a higher weight. As the loss gets closer to the optimal loss, the weight is lower. With this approach, we accommodate the differences in loss scales across datasets, encouraging the model to minimize reconstruction error across different datasets in a balanced and coordinated way. Our results show that adaptive weighting is able to improve the total reconstruction accuracy over the core integrative model. This figure shows that the total reconstruction accuracy versus alpha, a strength factor that controls the adaptive weighting. The blue line is our adaptive weighting reconstruction accuracy across a range of our values. They are consistently lower than the core integrative model, shown in the gray dashed line. The orange line is a baseline method, which is based on Liu's dynamic weight averaging method, proposed originally for multitask learning. Our method is consistently better than the baseline for an unsupervised setting. To remove bias from the data representation, we expand the core integrating model to add two fairness components. The first is a disentangling component shown in the orange box. The sensitive attribute S, for example, an income map, is passed into the decoder. The idea is to separate S from the rest of the information in the EquiTensor. The second component is an adversary. An adversary is a submodel that predicts S from the EquiTensor. It acts against the core integrated model that tries to recover everything from the EquiTensor. The whole model has two objectives: minimizing the reconstruction error and maximizing the error of the adversary. We use a strength factor lambda to control the trade-off between the two. The ultimate effect is that the sensitive information is removed while other information is retained maximally in the resulting EquiTensor. The entire architecture is trained jointly to optimize for reconstruction accuracy and fairness. We use mean absolute error MAE to measure the reconstruction accuracy of EquiTensors as well as downstream prediction accuracy. For fairness, we measure upstream fairness and downstream fairness. Upstream fairness is for integrated representations. Downstream fairness is for downstream predictions. We evaluate upstream fairness using an independent model, also known as an independent adversary. An independent adversary tries to predict a sensitive attribute from the data representation. Higher prediction accuracy suggests that the representation contains stronger association with the sensitive attribute. We evaluate the fairness of downstream predictions that use the EquiTensor or any other features. We use residual difference RD and its variance, positive residual difference PRD, and negative residual difference NRD to measure fairness. The idea is to measure the gap between the prediction errors between two demographic groups. Now let's look at the results. This table shows the accuracy of predicting sensitive information, race and income from representations generated by different models. The top section contains the fairness agnostic representations. The second section contains two baseline representations with fairness treatment. The third section shows the results of our EquiTensors with different lambda values. Lambda is a strength factor in the objective function that controls the trade-off between reconstruction accuracy and fairness. We can see that the sensitive information S was detectable with much lower error in baseline representations than with EquiTensors. This suggests that EquiTensors have weaker correlations with the sensitive attributes than fairness oblivious baselines. And the EquiTensors are fairest of all other representations in the table. We now look at the downstream predictions that use various types of external features. For crime prediction, we want to remove the effect of race. We first look at a non-exogenous data baseline model, which only uses historical crime reports to predict future reports without any external data sets. We also look at an oracle model. The oracle model uses hand-selected features that are known to be predictive to crime report prediction. This should be an optimal model that will produce the best accuracy among all other baselines. We then consider two baseline representations, PCA and early fusion, for producing integrated representations. We can see that we can see from the prediction accuracy that using external data can help with prediction performance compared to the no-exogenous data model. Our EquiTensors outperform baselines and can help the downstream to achieve performance comparable with the Oracle model. For fairness metrics, RD and PRD, the closer to zero, the better. We see that predictions with EquiTensors are more fair than models with fairness oblivious features. For backshare case, we want to remove effect of income. We see that with EquiTensors, prediction models outperform no exogenous data model, suggesting that EquiTensors can provide useful information for the predictions. Let's look at the fairness. Again, lower absolute value suggests fair predictions. We see that using fairness oblivious external features may introduce additional bias to the prediction results. With EquiTensors, predictions are overall fair, more fair than the, fairness agnostic representations. However, we observe large deviations of RD and NRD. The reason could be that the fairness metrics are not precise or they are influenced by the threshold that defines the advantaged and disadvantaged groups. It is also possible that the transferability of EquiTensor's fairness is not strong or stable for the backshare case, as we did not explicitly optimize over RD or NRD in the downstream predictions. The downstream models sometimes may still be able to pick up and exaggerate the remaining information about the sensitive attribute if the predictions heavily rely on it. So to summarize, we found through the fairness metrics that exogenous features might introduce additional bias to the prediction results. And the proposed EquiTensors can help counteract bias in data while helping the downstream task improve prediction performance. Looking ahead, EquiTensors represent a promising approach for broadening the utility of open data protocols, making them safer and easier for downstream reuse. Lastly, we will go over limitations and future work. The paper uses a fixed grid partition of spatial data. The advantage of grid partition is that we are able to use convolutional neural networks, and it is easier to define fairness based on a uniform partition. Future work could explore how to make use of multi-resolution information and handle sparse data. It is also interesting to look at other types of data representation. For example, it is natural to represent row networks in graphs. Convolutional neural network is promising in handling this type of data. And in this paper, we use Seattle as a case study and focus on spatial temporal prediction tasks. It is interesting to see how we can transfer EquiTensors to other cities and to other applications. Transferability of fairness is even trickier. Through EquiTensors, we show that fair datasets may help you restrict the propagation of sensitive information to downstream applications, but our results are only suggestive because we rely on purely empirical data. More research is needed to verify whether the transferability holds for other applications and for other non-spatial temporal domains. Current research in fair machine learning focuses mostly on technical aspects of fairness. This paper takes one step further to bridge fair machine learning methods and application domains. However, there are many issues that deserve further investigation. For example, the statistical notions of fairness do not equal to equity goals in the real world, and there are many conflicting fairness metrics. And the interpretability of deep learning-based method is still lacking. And however, interpretability is related to transparency, accountability, and fairness when it comes to decision making. Some methods could help explain the model behavior like visualization, model translation, and attention, but it is still an ongoing research topic. That is all for our talk. Thank you for your attention.